So yeah, I'm going to use the next 5 minutes to just talk about what I've been doing during my PhD. I've been designing, modelling and manufacturing composite hydrogels for biomedical applications. And so in terms of the actual application, I'm addressing the challenge of osteoarthritis, which is a degenerative joint disease affecting mostly over 60s, but it also can be affecting younger people as well. It's significantly affecting their quality of life, independence and mobility, with the current treatment plan looking at basically pain management up until all mobility is lost and then the joint is replaced with an implant. And so that is a generation 1 implant at the moment, which is bio-inert materials such as metals and ceramics, usually titanium. There was a brief look into generation 2 implants, which included bioglass. However, that wasn't too effective. And then currently we're looking at generation 3 implants, so soft material scaffolds that can support cell growth and hopefully induce regrowing of the articular cartilage whilst load bearing within the joint. So specifically the materials that I look at are firstly a natural-based polymer backbone, gelatin methacrylate, and a synthetic-based polymer backbone, which is polyethylene glycol diacrylate. Both of these systems are tested with and without a supporting network to address the composite aspects, and that supporting network in both cases is an alginate polymer. And so the initial network formation is carried out using Igricure 2959, which is a photo initiator, and that allows for the 3D network to form through a UV cross-linking reaction, which could then potentially be pushed through 3D printing to manufacture more rapidly. And then this 3D network is then submerged in the alginate solution, which forms a semi-interpenetrating network, which is then cured ionically. Finally, I also look at a range of different additives. I've worked with a master's student designing bespoke spring-like proteins which can be used to absorb the compressive load within the 3D network, and also hydroxyapatite and nanoclay nanoparticles, and they're mainly used to improve the fracture resistance of the materials. The overall methods for my PhD fall into 2 main categories which feed into each other. So firstly, it's the experimental, which involves physical and mechanical characterization, such as determining the linear viscoelastic region. So this is key, as when the material is in a joint, it must always be operating within its linear viscoelastic region, so there's not irreversible damage to the material. The swelling characteristics are important within the body, and also mechanical characterizations such as compressive strength and fracture resistance, including other properties as well. At the bottom you can see the graph on the right is stress strain of these materials, also looking at the area underneath for the energy absorbed, and on the left you can see a microindentation, so we can map the surface properties, and that is a map of the Young's modulus across the surface. These material properties can then feed into the modelling, and so I can generate hyperelastic material models that can then be tested, and so I've reconstructed a hip joint from CT scans within Abacus, and then I will insert the models into the joint to test their material properties and run parametric studies. And again, so this informs the experimental direction to move that forward. In terms of the future work, I plan to carry out further fracture resistance testing and looking at how additives improve the fracture resistance. So this is a combination of the fracture toughness of the material, which is the point at which the crack propagates, and also the energy release rate, which is the rate at which the energy is released through crack propagation. More simulation testing, the fatigue life of the materials, so the materials must undergo many cycles of loading, and finally harvesting real human articular cartilage and running micro indentation testing on this to compare to my soft materials. So that's the end of the talk. Thanks for listening, and come find me at my poster.